Good afternoon and welcome to today's webinar on EV battery manufacturing, presented by Hexagon and hosted by Metal Forming Magazine. My name is Brad Kuvan. I'm the editorial director at Metal Forming Magazine and the Precision Metal Forming Association, and I'm pleased to serve as your moderator today. Before we get started, just a few notes about today's go-to meeting. The meeting is being recorded for archiving, and the recorded event will be posted to our website within the next few days. So we will let you know via email when that recorded webinar is available online, and you can share it with others at your company and perhaps rewatch it yourself. Also, all participants in the meeting are in listen-only mode. So this means that the speaker and other attendees will not be able to hear any audio from your site during the program. However, you do have the ability to communicate with us throughout the program by submitting your questions and comments using the question box located on the right-hand control panel on your go-to screen. So you'll simply type your question to an organizer as selected from the drop-down menu. Then you'll use that same question panel to ask questions of our speaker at the end of the presentation. So we'll go ahead and begin today's webinar where we'll discuss battery cell, module, and tray manufacturing, including assembly, while focusing on managing the quality issues that can arise during the production process. We'll also learn how virtual manufacturing can play a vital role in achieving consistent, high-quality production, including tools such as virtual forming and virtual assembly. Our speaker today is Michel Perim, Director of Global Channel Business at the Hexagon Virtual Manufacturing and Costing Center of Excellence. Michel began his career at Transvalar, which is a French material forming simulation company. He then started his own company as a business partner for US-based SFTC company, where he was responsible for introducing deform to the French-speaking countries in Europe. During the past 6 years at Hexagon, Michel has been advocating best practices for additive manufacturing simulation, and since 2019 as Director of Global Channel Business, his focus has been on material forming and the additive manufacturing simulation. So please welcome Michel.
Thank you. So can you hear me clear?
Yep, sounds perfect.
Okay, very good. So thank you for the introduction. So the topic of this webinar, as said before, is about EV battery manufacturing. Sorry. Okay, so the contents and the agenda today is, first of all, I'll start with a short introduction about Hexagon. Then we'll describe the fundamentals in the EV battery manufacturing. Then we'll go through the steps of EV battery manufacturing and the challenges. And then we'll go through the solutions we can provide in virtual manufacturing and assembly. And I'll conclude this webinar. So Hexagon is a Swedish-based multinational company with over 20,000 employees across 50 countries. The revenue in 2020 was about 4 billion euros, and it focuses on autonomy in different aspects. And we are committed to innovation with more than 4,000 employees in research and development. The idea behind Hexagon and the mission is to go from mechanization to mass production and in the end to autonomy, so full autonomy, profiting from the data. And Hexagon is actually originally a sensor or metrology company. Then it acquired many companies in the software area. And in fact, the idea is to connect the virtual world and the physical world. So just to make it a little bit clearer, in fact, Hexagon, as I said before, acquired many companies, and One of the companies Hexagon acquired back in 2017 is the well-known MSC software in the US. And MSC software is now, I would say, named as design and engineering within Hexagon, and specifically one Hexagon division, which is called HMI, for Hexagon Manufacturing Intelligence, where we have different business units. And just to make it very clear, what I'm going to describe today and to explain we'll be focusing on manufacturing simulation, and this is actually this center of excellence. So as was said in the introduction, there are different centers of excellence within design and engineering, or MSc. One of them is called virtual manufacturing and costing. So that's the I would say the center of excellence I belong to. And this center of excellence is actually the merge, or the merge of FTI, so Forming Technologies Incorporated from Canada, Simufact, which is originally a German-based company, and another company called Amendate with a I would say additive manufacturing topology optimization software. So what we do here is we focus on process simulation. So from sheet metal forming, so that's basically FTI with cost optimizer for cost engineering, then forming suite for sheet metal forming, I would say based on shell elements. Then we have the Simufact product suite, Simufact forming. So with Simufact forming, one can model many kind of forming processes, such as hot forging, cold forming, sheet metal forming, rolling, ring rolling, heat treatment, and so on. So all this based on for metal-based processes. Then one module of Simufact forming is called joining optimizer. So in Simufact forming, we can simulate also mechanical joining, like riveting, clinching, self-piercing riveting, and so on. Then we have a software solution for welding simulation. So here we can investigate distortions and residual stresses of any kind of welding process, such as arc welding, laser welding, electron beam welding, or spot welding. And we can investigate based on some welding strategy, so welding direction, welding sequence, power, velocities, and so on, how the structure is going to behave in terms of distortion and residual stresses. Finally, we have a nice and comprehensive solution in metal additive manufacturing with Apex generative design first, that would optimize topologically a part so that we get the lightest possible part to withstand some stresses or some loads. And then Simufact additive to simulate the powder bed fusion process or metal binder jetting process, so which both are additive manufacturing processes. So on the right-hand side, you can see some animations. So basically, FTI products are based on shell elements, so they can provide information, and we will see that next in the presentation, at a very early stage, information about risk areas where you can get tears or wrinkles, and it can also provide information about costs, so and also the best nesting strategy, and so on. Then with the Simufact product suite, we can investigate in more details the material deformation and risks. You can see different animations here such as bending processes or coining or wire rolling. We have also hot forming or hot pressing, also roll forming processes and spinning. So the important thing to know is that Simufact is based on solid elements. So most codes on the market are based on shell elements for sheet metal forming, but Simufact forming is actually based on solid elements. So the advantage is that first we can simulate many more processes where with very strong thickness evolution. Plus, one example is spring back, so we can capture spring back much better than shell element-based codes. Right, now if we go on to EV battery manufacturing and the fundamentals, I would say that if we look at the cells themselves, we have, generally speaking, three types of cells. So the cylindrical cells, the prismatic cells, and the pouch. For each kind of cells, there are, of course, advantages and disadvantages. For the cylindrical cell, it's low density, low cost, easier thermal management, and hard casing. Prismatic, optimal density, large size, thermal management has to be carefully taken care of, and there is also a hard casing. So for the first two types of cells, so cylindrical and prismatic, we have solutions, and I will introduce these solutions in the next slides. The third one is a pouch type of cell, and for these kind of cells, we currently do not have any solutions because there is a soft casing, and it's something we are not covering right now. Then when we look at the modules are also different for cylindrical, prismatic, and pouch. So we will go much more into details during this presentation, but about the cylindrical cell, it's quite easy to manufacture. The density is quite low. As we said before, the thermal management is easy, and there is little or no expansion in the metal case. For the prismatic, there is optimal power density, and again, challenging thermal management, but here we have solutions in terms of simulation. Then the packs. So once the cell have been manufactured and put into modules, we need to assemble them into a pack. Be it being the cylindrical cells or the prismatic cells, it's quite similar. The modules have to be loaded into the pack and welded and sealed. So now, what are the manufacturing steps of all these different cells and modules and packs? And this is what we are going to look at more deeply in the next slides. So for the cells, we have different manufacturing processes such as forming or stamping or extrusion, then cutting or trimming, joining, and some chemical process operations that we are not covering with our solutions. About the modules, again, we have some stamping or sheet metal forming or deep drawing, welding, and mechanical joining. And finally, for the assembly or the pack or tray, there are again some stamping operations or deep drawings, some castings, weldings, and joining. So if we look at the challenges with the manufacturing process, as you saw before, we are covering many other processes and segments, industry segments. But for the EV battery manufacturing, I would say the challenges are very similar to other industries. So it's a long development time. There could be some reworks or engineering change orders that are very costly. Some processes can be designed and be very unstable or with a very narrow robustness window. There is, of course, material waste and costs. Tooling is an issue. So tool life, how many parts can we manufacture with one tool set, and quality issues such as cracks or important thinning and so on. So there are a lot of challenges that need to be tackled in the EV battery manufacturing. So what are the solutions that we can bring there? So I'm going to go through some case studies about each segment, like battery or module or tray. So at Hexagon, and especially the virtual manufacturing and costing center of excellence, we offer a suite of solutions or software that can help tackle these challenges that we just mentioned before. So the first thing is the virtual tryout. We have solutions to, instead of spending a lot of time doing physical tryout and cutting some tools, machining some tools, trying on the press, for example, the stamping or on the weld side, the welding, we can do all this in the virtual environment. And we have solutions for that, such as semi-fact forming, mechanical joining module, or FTI cost optimizer, semi-fact welding, and MSC Apex. All these products can be used, and of course, we can chain the simulations, meaning that we could simulate one process, such as stamping or deep drawing, and then export the results into the welding tool, for example, keeping the residual stress or the strain information inside the mesh. Then we can check for early forming feasibility. Even before you have design or you design the tooling, you might want to check, okay, is this part feasible, or is formability guaranteed? Will I get tearing or any other kind of problems? And for this, we can use FTI Forming Suite to check all these early steps. Then in the welding process, the typical defects are distortions or high residual stresses, and we can check all these at a very early stage using our simulation tools. Then we can also identify with our solutions the inefficient designs, such as not optimized nesting, for example, or processes that are not stable enough. Forming Suite from FTI also brings some cost estimation. So whether it is used by OEMs or by tier 1, tier 2 suppliers, customers can, at a very early stage, estimate costs for tooling and for material and optimize the material utilization. Yeah, and then for more suppliers like tier 1, tier 2, we can provide tools to estimate again the cost, and then that's could be a very good tool for quoting and sales departments. So in the end, the whole purpose of using virtual manufacturing is to save time and obviously money and resources such as material or energy. So now if we go through the different steps or areas such as battery, modules, and packs, I will show now some examples of how simulation can be applied to these steps. So as we mentioned before, the cylindrical cell assembly consists of forming and assembly processes. So a very basic workflow is described here. So you can see the battery housing could be extruded, then the cap is stamped, then there is a trim process for excess material on the housing, and there are then some chemical processes such as inserting the jelly roll and insulator, welding the terminal to the cap, or fill the electrolyte, so that would not be covered by our solutions, and then finally roll the cap onto the cell housing. That's the process workflow. The relatively similar process can be applied with prismatic cells. There is an extrusion process, so backwards extrusion, where we then trim the excess material. We have examples that I'll show in the next slides. Then stamp the lid, do some chemical or chemistry operations like insert the jelly roll and insulator, weld the terminals to the electrodes, and then clinch the terminals to the lid, stamp the terminals, weld the lid, and then finish with the chemical operations such as fill electrolyte and seal the venting cap. So now I'm going to show some examples, some simulation examples. One thing I didn't mention in the early beginning of this presentation is that all our solutions, semi-fact forming or FTI, are basically process-specific applications. So they are based on, especially semi-fact forming is based on the MSc Mark solver, but the user interface and the GUI is actually very easy to learn, and it doesn't require very deep knowledge of numerical sciences or FEA. It's used on a daily basis by I would say die design or process design engineers, even CAD engineers or designers who use on a daily basis CAD software. So here we can see the stamping of the lid, sorry, of the cap, and we can see the whether there are some underfillings or some excessive thinning, and of course at the end of the simulation we can see the spring back. Then the cap is rolled onto the housing. So here we can determine or optimize the number of rolls that are required, and also try and minimize the number of revolutions in order to complete this process. It is obviously clear that reducing cycle time or any other, I would say, parameter would lead to huge cost savings. We are here talking about millions or billions of batteries produced each year, and of course, cycle time is an issue or a challenge. About the prismatic cell, as we said before, we start with a backward extrusion. So here, using semi-fact forming, we can simulate this process quite well and see, for example, so the process is there is a punch, there's a die container, and we would form or extrude that billet or that strip to get this square shape or rectangular shape. Then, so what can we expect from the simulation is obviously the final shape, and see where we need to trim, or if we need to perform a second extrusion operation, and also get a feel or information about residual stresses. These residual stresses will have an impact, of course, on the welding stage later. Another component of the battery is the lid. So here we can simulate the forming of the lid and also the trimming. So here we haven't performed trimming, but it's possible in simplified forming to do also trim operations and evaluate the impact of the trimming on the final shape. So it could be just trimming or fine blanking. So again, in this stage, the user can, in a very early stage and even before manufacturing the dies, optimize the this stamping and investigate spring back and residual stresses. About the terminals, we can use semi-effect forming also for some connections or connecting the terminals to the lid. This is a kind of clinching operation, and this can very easily be performed using semi-effect forming. So here again we have a blank holder, we have a die, and the terminals. So what kind of information can we get here? Of course, the material flow, then the quality of the connection. If I use so much stroke, then how is the material going to behave, and how good the connection will be between the lid and the connector. Of course, in the battery manufacturing area, we need to have very sealed components to avoid humidity or water to get in the battery, or the chemical to leak out the battery. Then once we simulate all these forming processes, we can use the welding simulation software and import the results of the forming stages into the welding stage, and investigate distortions, residual stresses, and what could be the best workflow or the best, I would say, clamps or clamping system to minimize distortions and improve quality. So there are, again, thermal aspects. So we could investigate, for example, overheating, or also the heat affected zone in the battery, in the cell, and also mechanical aspects such as distortion under the condition that we would weld from one direction to the other, or the welding sequence could be optimized virtually before even trying it in the workshop. Right. So that's it about the battery cell manufacturing. Then once this is done, or many customers, of course, don't manufacture batteries, but maybe battery modules. So we have here again some solution, or our solutions can be applied to this kind of process. So again, a simplified manufacturing workflow would be to form the sheets of the module tray, then assemble them. So here we used, as an example, some riveting. They could be also welded, but in this case, we are showing a riveting. And then the cells, so in this case, the prismatic cells are inserted into the modules, and typically they would be bonded with some adhesive material. So in seam effect forming, we have a special module called mechanical joining that would investigate different kinds of mechanical joining processes, such as blind riveting, or in this case here, it is called self-piercing riveting. And in this battery module, we can see that the customers used this self-piercing riveting to connect the different sheets. So this module allows for the prediction under different conditions. For example, different sheet thicknesses or different materials, predict the behavior of the sheets and the rivet, and assess virtually the quality of the joint. So there are some, I would say, different criteria to assess the joint quality, such as interlocking, so the penetration of the rivet inside the lower sheet, or also the residual thickness of the lower sheet. And these criteria are well known. Seam effect forming joining module allows for the I would say the automatic evaluation of such joints. Then the prismatic cells are bonded together using some adhesive. So here we can use seam effect forming to predict the behavior or the flow of the adhesive material. So this adhesive material also plays a role in thermal management. And we can see here the location of the adhesive material when pressing or the batteries together, and evaluate, okay, do I have enough adhesive? Is it located in the best place or best location? And all these investigations can be done virtually. So that's a summary of what I just said. And on top of that, not only can we investigate the location or of the adhesive material, but also loads. So what is the load that I should apply to these batteries in order to get the right location of the adhesive material. Finally, we are now moving on to the tray. So we saw our solutions in the cell manufacturing, in the module manufacturing, and now we are going to look at the tray manufacturing. So there are different technologies, but one of them could be deep drawing or stamping of the tray. So in this case, you can see the size, so about 2.4 meters, 1.8 meters wide, and 2.4 meters long, with a weight of 58.7 kilograms. So it's not necessary, or it's not easy probably to determine the true weight without doing any simulation or physical testing. So using forming suite from FTI, we can get a lot of information at a very early stage. And one of them is the material utilization. So this solution can give you, can optimize the nesting, for example, of the sheets on the coil, and optimize material utilization. Of course, here we are talking about hundreds of thousands or millions of parts. So if we can like save even 1, 2, 3% material, it will amount in millions of dollars. Then FTI forming suite will give you, at a very early stage, even before manufacturing the dies or cutting the dies, valuable information about thinning, so residual thickness in the corners, for example, or risks of tearing or wrinkling, and so on. it's in fact sometimes products are designed without, I would say, taking into account the challenges or the specificities of the manufacturing process, and this could lead to changes in the design of the product, because the product is not, I would say, manufacturable, or the manufacturer side is a problem, and customers need to redesign their products by taking into account these challenges of the manufacturing process. So that's of course a disaster, and that's why using our solutions in a very early stage can minimize this risk of having to go back to the CAD and to redesign the product, because it's simply not possible, or the robustness window for the manufacturability of the product is too narrow. Then FTI can also give very valuable information about planning, process planning, how many steps, how many stages, and so on. And this also, of course, has an impact or an influence on the cost, on the final cost of the part. So the earlier you know what kind of issues you would have and how much it will cost, and of course the better it is for process robustness and cost savings. So that's an illustration of what I was just mentioning before. We can see here the material flow of this battery tray stamping, and also the thickness strain. And also recently FTI developed this 3D addendum, so the I would say generate the tooling based on the final shape of the part. Then the results. From the latest versions, we are able to import into SimUFACT welding. So when we want to simulate the welding of this tray, we can use FTI forming suite and use the result as an input into SimUFACT welding, and then getting, of course, more accurate as if we would use only the CAD or the ideal shape of the tray. Now we are able to import simulation results, which are actually much closer to the actual parts or to reality, into SimUFACT welding. So SimUFACT welding, as I said earlier, is a process-specific software that covers, I would say, welding, any kind of welding operation, and the purpose here is to predict distortions and also residual stresses. So we can see on the left-hand side the displacement, and we can see in some places displacement is about 1.2 millimeters. We need to know that prior to weld the tray, of course, and this tool gives us this ability. We can also see at the end of the welding process the residual stress, and as you may know, within the MSC software portfolio, we have different capabilities such as structural analysis with Nastran, or we have fatigue analysis using CAE fatigue. And it's possible to export these results, so residual stress results from SimUFACT welding into these MSC packages to take into account residual stresses in these subsequent analysis. And here we have a, I would say we can scale the displacement. So the real displacement is about 1.2 millimeters, but we can use the scaling. So in this particular case, a scaling factor of 50. So we can see the trend, and we could also think of compensating the shapes. That is to say that we could think of in the stamping stage, stamp the tray in order that after welding the distortion would be more or less zero. So if we can predict the behavior of the tray during the welding process, we can anticipate it and stamp a tray that has such a shape that after welding it would be flat, or the distortions would be minimized. So I'm now coming to my conclusion. I think we could discuss in this webinar that we have different tools as Hexagon to predict in a very early stage the behavior of the material, and to optimize also the material utilization. And whichever the process may be, we have a solution to simulate in a very easy way and relatively fast, and sometimes very fast way, the forming or the welding or the assembly, joining of different components. Starting with FTI forming suite, Simufact forming, MSC Apex for mesh generation, Simufact welding for welding simulation, and the joining modules of Simufact forming for any kind of riveting or mechanical connection. So if you are interested, you could visit the MSC Software website under www.mscsoftware.com/industry/e-mobility, or scan this QR code. Then you could download videos and also flyers that would summarize or give you further information about our offerings and solutions in the EV battery manufacturing or EV battery enclosure manufacturing areas. Thank you for your attention, and I'm open to answer any questions.
Outstanding. Thank you, Michel. So we do have about 15 minutes left for questions. You can go ahead and write your questions, using that question panel on the control screen. So the first question, Michel, has to do with spot welding. Do you know what components within the cells or trays, what have you, are resistance welded? Are they using laser welding all over the place? Or are there applications for resistance welding, to your knowledge?
Yeah. Okay. So I just gave some examples of what we have seen on the market, but as I said, Simufact welding is able to simulate, and in fact very well. We did some experiments in Europe, not only about the distortion, because distortion is easy to measure, but also about residual stress, where the customer was actually taking the structures to some synchrotron, or to observe or to measure residual stress. And we could get very good agreement or very good correlation between the residual stress in the nugget from our simulations with Simufact welding and the experiments. So yes, we can definitely, I would say, model the resistance spot welding process. Now it depends on each manufacturer to choose, okay, which process he will, or which technology he will use. I've seen also some laser welded trays. So this also we can we have a special module for laser welding, and that could be investigated using Simufact welding.
Okay, good, thank you. One of the questions is will there be a copy of the presentation available? Yes, so we will, if you agree, Michel, we'll go ahead and make this presentation into a PDF and send it out to the attendees. And then the recording of the webinar will be on our website within the next day or two. So we'll send an email out to all the people that registered with a link to that recorded webinar. Question is, how does the simulation software account for lubrication in the forming process?
Okay, so we have different ways to account for lubrication. As you all probably know, there are, I would say, friction laws, such as Coulomb or shear or combination of both. And of course, this can be set in the software. We have experimental values. We could, in the software, we have also a kind of library with different friction factors for different processes, such as bulk forming or sheet forming, hot forming, cold forming, etc. So that's one thing. And the second is, of course, as for any kind of simulation software, there is at the beginning of when people start using it, I would say that there is a kind of learning curve or kind of calibration stage where the user can actually fine tune the friction laws or the friction factors. And we are here, obviously, we have we have Simulfact specialists and experts in North America, and the MSC Software is based in California. I mean, it's a US company, so we have people there to guide and to handhold the users and get them started as fast as possible using the software. But we do have a lot of capabilities when it comes to friction.
Excellent. So, little tricky question. Maybe you'll be able to address it. What's your understanding on the root cause of the recent GM Bolt recall? And if you know what the root cause was, are you able to catch issues like this in the battery manufacturing process? So, are you familiar with the Bolt recall?
Sorry, no, I'm not really aware of this. Can you explain a little bit more? Or?
Well, I cannot, but maybe the person that asked the question has a little bit more insight. He can add. In the meantime, yeah. Or he can email you directly. Your email's on the screen there.
Exactly.
So the next question then is, can you simulate dual phase materials?
Yes. So you mean multi-phase materials? You mean?
The dual phase steels, the new steels. I assume you can do simulation on those materials?
Yes. In fact, we have. So the solving is actually thermal, mechanical plus metallurgical. So we can also solve the metallurgy changes equations with TTT diagrams. We have the database consists of about 750 materials, metallic materials, and some of them have or contain metallurgy changes or TTT diagrams, so that during the welding process, for example, we can see the different phases after cooling.
Very good. What do you know what the expected life of these EV batteries is? Obviously, that's changing and improving. But how currently?
No, I have no idea. In fact, I'm I'm into manufacturing of batteries, and I don't know anything about life.
Sure. Right.
Maybe there are some people at MSC or Hexagon that know about this, but
sure. Right. And then the follow-up question is, how are they recycled? Which you probably don't know much about that either, I would imagine. Okay. Does this one you can answer? Does the software have built-in thermal models of a battery based on its chemistry or the technology used to manufacture it? You have built-in thermal models.
Not directly our VMNC Center of Excellence, because we are focusing solely on the manufacturing process. Then the battery life cycle and everything, is not covered by our COE. We focus on manufacturing issues, in fact, not like life of the battery or the only thing we focus on is when it comes to thermal is, for example, the elevation or the temperature increase when we form the material, for example, or when we weld it virtually. Then we can see, of course, the temperature distribution and the cooling rate or the cooling time. but now when the battery is in service or is working, is in operation, we don't know. I mean, we as Simufactor or FTI, our tools are not designed for that. There are probably other MSC software tools that can simulate this, but not ours.
Okay. Okay. Do you have any comments on the use of AI when it comes to observing and understanding the metallurgical phases?
Okay, well, as I said, we have models for phase changes, and that are depending on cooling rate, carbon content, stress state, and all this. We do have within the Hexagon group, we acquired recently an AI company, which is called Catalan. So there are works about this, but it's ongoing developments. As I said in the introduction, Hexagon is focusing on autonomy, and AI is obviously one big brick of this autonomy and data mining and analytics and AI. But it's still under ongoing development.
Okay, good. Thank you. Are you aware, Michel, of any trends in the use of the different types of battery cells that you described today? Are they specific to certain OEMs, or any trends in how they're being made? More complex stampings, for example, or different types of metal alloys? Any trends that you're seeing in how the cells are being made?
Yeah, what I know is that there were in this presentation previously there were OEM names, but for obvious reasons we cannot name them in this presentation. But it's true that it seems that the trend is more towards pouch or prismatic or pouch. So the cylindrical cell is a bit passé, or maybe I'm wrong, but that's what I feel. It's the developments are more into prismatic and pouch.
Okay. And any changes in the types of materials or gauges or complexity of the parts?
Well, we see a lot of aluminum, but as I said, again, we are not. We are focusing on the manufacturing, so it means that the customer needs to come up with some design, and then we can check out virtually whether this design will stand, will be sustainable, or whether it's possible to manufacture this or not. But I'm nobody to tell you about the trends, and we do have people. I do have some colleagues who are much more into the trends and who look on the market, and I give you some contacts and everything, but I'm really focusing on the manufacturing process.
Sure.
That's where I'm.
Okay. Can the software, can you simulate blanking and trimming operations?
Yep. So absolutely, we can. Of course. Okay, in this presentation, I did not get the opportunity to show this kind of capability, but I wanted to stay focused on the EV battery manufacturing and with some specific examples. But of course, we do have some trimming or fine blanking capabilities within Simufact forming, and many of some press manufacturers who are specialized in fine blanking, for example, are using our software.
Sure. Okay. We do have a few more minutes left. If anybody else has questions for Michel. So if the simulation identifies a problem at any point in the process here, does it recommend solutions, or how does the user go about kind of correcting a problem that might come up in the simulation?
Okay, so I would say it depends on which solution we are talking about, but basically the answer would be no. So the software does not replace the engineer. know-how is with the engineer or the designer, and the software is a kind of validation tool. So it's what we call it a what-if system. So it's a what if I do this, then what's going to be the outcome? What if I weld, and welding is maybe not the perfect example, but informing, what if I use, I don't know, this thickness, this stroke, this friction, this location or positioning within the dies, or if I use pre-stressed dies, or spring-loaded dies, what is the pre-stressed state I have to apply, or whatever, what was going to be the output. So I would give the software an input, so input parameters, and then the software will give us some output. So that's the rule. Now we do have some solutions, and especially with welding, we have a partnership with a company, and we could suggest, or this I would say module would suggest it's called welding sequence optimizer. So it would give us I would say the best or the optimum sequence. So what should I start with this beam, with that sheet or that plate, and then the software would recommend, I would say, or would suggest the best welding sequence for the assembly to minimize distortion. Yeah.
Right. I got you. Okay. Can you comment on solving time? I guess for the stamping example, since you're using solid elements.
Okay. Well,
runtime?
Okay, solving time is always very it's a tough question, because it depends on many I would say parameters, such as mesh size, then parallel processing. So we do offer parallel processing capabilities. We also offer so okay, for FTI solutions, the solving time is very fast. If we come to solid elements and simufact, obviously it depends on the thickness, the aspect ratio. So if, of course, there are some parts that we will not be able, or with a lot of problems to solve, like panels, like hood, or parts that are very large but with a very thin skin. So that's typically if I may name the competitors, like Autoform, or PAM Stamp, or even these are typical parts, technically speaking, for this kind of simulations. Now, if we look at more structural parts, or where the solid meshing is actually makes sense, then we would have much better results than the standard approach, shell element approach. And the solving time is not that is not such a problem anymore. We can use parallel processing. We have like optimum meshing strategies. We have a specific mesher for sheets, where we could give the software a number of elements that we want to have in the thickness, and then the mesher will just mesh that sheet accordingly.
Sure. Okay, good. Thank you. Next question, does your welding simulation account for the pulsing mode, or what he's calling a wobble shape? Does it account for pulsing?
I'm not sure. I don't really get the question. Pulsing mode meaning in the heat generation, you mean? You mean?
Well, there is a pulsed welding. There are weld schedules that pulse the current. So I guess that's what he's asking.
Yes.
If you could
Okay, I understand. I understand. Well, in fact, we don't really take into account the way the heat is generated. In fact, the software, the heat input is actually an input. We don't calculate. We just need to get some information about how much energy is brought into the system. Now, the technology that is used to generate this energy is irrelevant, in fact. So if we can characterize, or if we can get information about the energy input or the heat input, then we are able to model the welding process.
I see. Okay.
Mm-hmm.
Okay, very good. I don't see any more questions, Michelle, so I think we can go ahead and wrap it up. So again, thank you very much for an outstanding and detailed presentation, and we want to thank our audience, of course, for attending. Everyone found it to be a valuable experience. Again, we will post a recording of the program on our website within the next day or two, and we'll send out an email to everybody with a link to that once it's up. Then you'll be able to review it again and perhaps share it with others in your company. So thank you again, Michelle, for a great presentation. Everyone, you can close your browsers, and we wish you a great afternoon.
Yeah, thank you all, and have a great afternoon.